Hello everyone, we are from the Advanced Materials and Device Engineering Lab. Today we will present our research on the development of high mobility double-layer oxide thin film transistors. Our team members are 권인우, 정서윤, 조유진, 홍광산. Our presentation is organized into three main sections: introduction, experiment results, and conclusion. We will first discuss the importance of oxide TFTs and the motivation behind our research. Then, we will move on to the experimental results, where we tested different materials, systems, and structures. Finally, we will summarize our findings and highlight the contributions of our work. Oxide thin film transistors, or TFTs, are a key technology in next-generation displays and electronics. However, conventional single-layer oxide TFTs face a fundamental trade-off. When we try to improve carrier mobility, reliability decreases due to oxygen vacancies. On the other hand, when we improve reliability, mobility often drops. This trade-off is a major challenge that limits the practical performance of oxide TFTs. The importance of oxide TFTs can also be understood from their wide range of applications. They are essential for flexible and wearable devices, which demand high performance under bending conditions. They are also critical for transparent displays and in-vehicle displays, both of which require excellent stability and uniform performance. In this research, our goal was to design and fabricate double-layer oxide TFTs that achieve both high mobility and electrical stability. We focused on optimizing the sub-layer composition and process conditions. By carefully controlling oxygen vacancies and interface trap states, we aimed to overcome the traditional trade-off between mobility and reliability. We began with a basic IgGO structure, which is widely used in oxide TFT research. To further improve electrical properties, we fabricated IgGTO by doping IgGO with 10 mol% of tin. Previous reports suggested that tin doping can enhance conductivity and stability, so we used this as a foundation. Next, we focused on dual-channel structures. This structure can significantly enhance device performance through two mechanisms: charge accumulation and interface effects. By combining a high mobility material with the dual channel effect, we aim to achieve much higher carrier mobility compared to single layer structures. The fabrication process for the double layer structure involved several steps. First, solution preparation and spin coating, followed by hot plate annealing. Then we used photolithography and etching to define the device pattern. This step-by-step process allows us to systematically study the effects of different materials and structures. First, we tested IGO. The results showed that IGO has poor carrier mobility, and the on-off ratio was also very low. Although its threshold voltage range was acceptable, the overall electrical performance was insufficient. Therefore, IGO was considered unsuitable for TFT operation. Next, we evaluated GTO. This material showed fine carrier mobility, a stable threshold voltage range, and a very high on-off ratio. Based on these results, GTO can be regarded as a high-performance candidate material for TFTs. We also tested AGO. Similar to GTO, AGO showed good mobility, a proper threshold voltage range, and a high on-off ratio. This means AGO also has great potential as a high-performance TFT materials. We then studied the effects of gallium concentration. When the gallium content was low, mobility decreased. As the gallium concentration increased, the mobility improved and reached an optimal level. However, when the gallium content was too high, the mobility dropped again. This shows the importance of carefully controlling gallium concentration. Finally, we tested IGGTO doped with 1% aluminum. The results showed fine mobility and a high on-off ratio. However, the threshold voltage shifted too negatively, which is a serious drawback. Because of this issue, the device is unsuitable for practical TFT applications. In conclusion, our work demonstrated three main points. Double-layer structures significantly improve both mobility and stability by controlling oxygen vacancies and reducing interface traps. Among the tested materials, GTO and AGO were the most suitable choices for the top layer. And compared to single-layer IGTO, double-layer structures using GTO or AGO achieved the highest mobility, proving the effectiveness of our approach. That concludes our presentation. Thank you very much for your attention.